You just saw how multi-vector approaches can be used in text retrieval. Now, let's build on what you learned and look at how a similar approach can be used in image retrieval. Alright, let's go! Image retrieval is important because a lot of useful information is not stored as text. It's stored in image files. Sometimes this means actual images, but scanned documents, PDF files or slide decks are also essentially images. A new generation of vision language models are able to accept both text and images as input. So if you retrieve the right documents, you can build capable multimodal RAG systems. The challenge is completing that retrieval step. Documents are the most common type of image companies want to retrieve, but they present a lot of challenges for retrieval. Slides or document pages can be a complex mix of text, images, charts, and tables. The traditional approach for parsing this kind of document is to first use special models to detect the layout of the document and then parse each content type separately. This approach requires you to build a complicated custom system that often is still fallible. What's worse, a retrieval pipeline for one kind of document often won't work on another. Callpally, a multi-vector image retrieval approach, addresses many of those issues. Callpally stands for Contextualized Linear Interaction over Polygemma. Polygemma is the name of a vision language model created by Google. However, the name Callpally is also quite often used to describe the whole family of models built on the same principles. Multi-vector embedding models built on top of vision language models, which can take both images and text as input. This is similar to Colbert, which is a specific model, but also is often used to refer to a whole family of multi-vector text retrieval techniques. Callpally has many great features. It skips the complicated and error-prone format detection step, and it works flexibly across all document types. While it can be somewhat costly to run, it can also end up being cheaper in the long run because your system is relying on a single model instead of many models that traditional approach relied on. Let's see how vision language models are adapted for retrieval and then apply them in practice. A typical workflow of a large language model goes as follows. Your input text is passed to a tokenizer. The role of the tokenizer is to split it into smaller units called tokens and to create a sequence of token IDs which is then passed to a model. In reality, the model translates these IDs into the corresponding token embeddings it learned during the training. Those vectors are static and specific to each of the tokens. For the time being, let's assume that the input of the language model is a sequence of token embeddings. The language model passes this sequence through its own layers and produces a contextualized embedding of the current token that takes the whole sequence into consideration. This vector is typically used to generate logits and then probabilities of each of the tokens in a vocabulary to be a continuation of the sequence. And vision language models are not different here if we use them for text generation. However, adding another modality requires some extensions of that architecture. Vision is an entirely different modality, so it cannot be converted into text directly. Thus, it has its own pre-processing pipeline, which obviously starts with an entire image. The overall goal is to process the image in such a way that you input it as a sequence of embeddings into the language model, like you do with text. So the image is being processed through an additional transformer which actually converts it into image patches of a specific size as a first step. A single image becomes a sequence of patches, not a single input. Similar to text, which is processed as a sequence of tokens, not as an entire document. Image input is passed through a neural network that is a vision transformer, and it again produces a sequence of contextualized vector embeddings, one for each input patch, typically highly dimensional. The output has to be then projected onto a smaller dimensional space and then passed to the language model. The reason for the last step is to make the image vectors have the same number of dimensions as the text vectors. All in all, this additional process enables a different modality to be passed to the same network. No matter the input modality, the language model will produce an embedding that will be used to generate logits and probabilities of each of the tokens later on in the generation process. So ultimately, a typical vision language model adds some extra processing to the images while keeping the text processing intact compared to pure language model. A VLM still predicts the next token given the input, so you are not done yet with the embeddings generation. You don't want a generative system, but something that will represent an input for the retrieval in the form of vector embeddings. In order to produce vector embeddings, you need to slightly extend the logic of the VLM and add another projection layer just right after the language model generates the hidden states from its final layer. This projection layer reduces embeddings for efficient storage. For Gemma, it goes from 2048 to 128 dimensions, but it may differ between the models. There is no pooling at the very end, so ultimately, the entire input sequence, no matter the modality, is transformed through a dot network and you get a sequence of the same length that represents your input. In general, it's not enough to just start using VLMs for vector retrieval. There is some additional training required for both the final projection layer and language model parameters. Many papers suggest using low-rank adapters to the language model attention weights. Low-rank adaptation adds low-rank matrices to the frozen base model. The term low-rank refers to the dimensional complexity, where a lower rank means the matrix can be represented as the product of two smaller matrices. For example, instead of training a full 2048 by 2048 weight matrix requiring over 4 million parameters, LoRa uses two matrices of size 2048 by 32 and 32 by 2048, requiring only around 131,000 parameters, which is a 97% reduction. The training process adjusts the whole model for effective retrieval, but due to these optimizations, it's easier and faster than full fine-tuning. Practically, you don't need to know all these details to start using ColPaly. You will start by loading the appropriate model based on available hardware. While ColPaly is a more powerful one, it requires a lot of memory to run, or even better, a GPU. For that reason, you can also use ColSmall, which is a smaller variant with 256 million parameters that you are able to use here on the deep learning platform. Feel free to run it on a different environment with the full ColPaly model so you can see the difference. No matter which model you end up using, you need a processor that works with raw data and converts it into a representation that the model can handle. Let's load a page from a famous Attention is All You Need paper to see how ColPaly processes visual documents. This PDF page contains diagrams, equations, and a lot of text. You will also use Pillow to load the image and check its dimensions. This high-resolution screenshot preserves all visual details from the original PDF. ColPaly processes images by dividing them into a grid of patches, similar to how a vision transformer works. For ColPaly v1.3, this is always a fixed 32 by 32 grid. For ColSmall, the grid dimensions adapt to the image's aspect ratio. Let's visualize how this particular image is divided into patches by adding some spacing between them. You have a helper method to do exactly this. Now, you will process the image through ColPaly's processor. This processor converts the image into a batch of tensors containing input IDs, attention masks, and pixel values that the model can understand. The processed batch contains input IDs that vary by model. It's 1031 for ColPaly or 1139 for ColSmall. Let's decode this to see how ColPaly represents the image internally. Notice the sequence contains 1024 special image tokens representing different patches of the image, followed by instruction tokens. ColPaly processes the image as a grid of patches, creating embeddings for each patch. For ColPaly, it's always a fixed 32 by 32 grid, while for ColSmall, the grid dimensions vary based on image size. Let's generate embeddings for the image. You end up with 128-dimensional vector for each token you just saw. For storage and search, we may prefer the embeddings corresponding to the image tokens, not the instruction tokens. Using a helper function to extract the image mask, we isolate this 1024 image patch embeddings. This number is fixed for ColPaly and might be different for ColSmall, but by a random chance, it's exactly the same number of patches created. One powerful feature of ColPaly is its interpretability. We can visualize exactly which parts of an image are most relevant to specific query tokens. Unlike traditional dense embeddings that produce a single pack similarity score, ColPaly's token-level embeddings allow us to see how each word in our query relates to different regions of an image. This makes the model's reasoning transparent and helps us understand why certain documents are retrieved. Let's explore this capability by creating a query and visualizing how it matches different parts of our document. We'll create a query asking about the transformer architecture. This page from the Attention is All You Need paper contains the famous transformer diagram, so we expect CallPaly to highlight those specific regions when processing our query. You will process the query through the model to get query embeddings. Each query token is also represented by a 128-dimensional vector, but there are just 21 tokens created out of this query. Let's clean it up a little bit by removing padding and argumentation tokens and then retokenize so we can see the individual query tokens to analyze them further. To create our similarity visualizations, we first need to calculate how many patches the image was divided into. You will also extract the image mask to isolate just the image token embeddings, excluding the extraction tokens. Now you will generate the similarity maps using CallPaly's interpretability tools. This computes the similarity between each query token and each image patch, creating a heat map for every token in our query. Please notice that we are actually trying to visualize the similarity of different image patches to the token containing layer. Let's visualize the similarity map for a specific query token. You will select the layer token from the query to see which parts of the image it attends to most strongly. This visualization will overlay a heat map on the original image with warmer colors indicating regions that CallPaly considers most relevant to this specific word. This interpretability feature is valuable for debugging and understanding your retrieval system. You can identify whether the model is focusing on the right content, discover unexpected matching patterns, and build trust in the system's decisions. In production applications, this transparency can also help explain retrieval results to end users. However, since we are using the smaller call-small model here, you can see that the model seems to be paying attention to some background patches, which is slightly unexpected. Let's see how it looks like for the full CallPaly model. This is how the same similarity map would look like for the bigger CallPaly model. Call-small performs some pixel shuffling, so the model was focusing on some random locations, but for CallPaly you can see the model mostly pays attention to the word layer, occurring multiple times on that page, which is expected, as that's the token you are visualizing. Let's build a practical multi-modal search system using Quadrant. We'll set up a collection with multi-vector support using MaxSim comparator to handle CallPaly's multiple embeddings per document. You will also disable HNSW graph creation, as Quadrant can't use it effectively either way. Now you will index all pages from the Attention is All You Need paper. For each page, we generate CallPaly embeddings and store them in Quadrant with the file path as metadata. Here we'll speed it up, but you can expect it to take a few minutes before you can see the end results. Let's create a helper search function that processes text queries and create CallPaly embeddings for them. The same function will also query the collection you've just created to get the closest matches. Since we are working with visual data, we have another helper method that displays the search results on the screen. Let's search for model architecture to see which pages of the paper the model considers to be the best hits. We ask for the model architecture, so it's not surprising that the most famous diagram is coming up first. But there is also a certain section of the paper which is called model architecture, so it's also selected as one of the best pages to answer that particular question. Next, let's search for scaled.product attention. Again, the diagrams in the first result returned are presenting exactly this, but there is also a part of the document which is called scale.product attention, and it also got captured by the CallPaly retrieval. Finally, let's search for experiment results. The goal here is to retrieve pages containing tables and performance metrics that we would expect the paper to contain. CallPaly seems to understand both textual content and visual elements like tables and charts. Surprisingly, the first page of the whole paper is returned as a top match, even though it doesn't seem to contain any kind of a table summarizing some experiments. Nevertheless, the experiment results could have been mentioned in the abstract or maybe in the footnotes of the article, so it's nothing that surprising. Nevertheless, the second and the third match They both contain some tables summarizing the efficiency of that particular method versus the other methods. And this is actually something we would expect from this kind of system to return. To sum it up, CallPally enables powerful multimodal search over visual documents without requiring an OCR step or complex document processing. By processing documents directly as images, it captures both textual and visual semantics naturally. Multi-vector representations come with certain limitations. Assuming each of the documents needs half a megabyte and you have 1 million documents, you may end up with 500 gigabytes of memory needed just to keep all the CallPally embeddings for search. That might be fine for low-scale projects with thousands of documents, but in practice, you often deal with billions of them and it would require a significant amount of memory to run. Having 1 million documents in a retrieval system is quite likely if your company has a lot of data to search over. Typically, these vectors will contain a lot of redundant information, and some interesting optimization techniques can help you reduce the RAM consumption. Let's discuss these methods in the next lesson.